Hello, and welcome back to QED and QCD. Now, we saw in the last lecture that the discussion of gauge invariance in QCD is slightly more complicated than in QED because of the self-interacting gluons. In fact, the gauge discussion in QCD is often taken not by choosing a Lorentz gauge, but by choosing a so-called physical gauge. So, physical gauges. And what does it mean to choose a physical gauge? That's a way of ensuring that only transverse degrees of freedom are indeed propagating. We don't get any longitudinal polarized gluons. Now, one way of doing that is to ensure or impose a gauge condition that requires that the gluon field A mu for each of the 8 gluon fields, A mu in mu is equal to 0 for a vector in mu. For some reference vector in mu that we can choose arbitrarily. Now, you can add a gauge fixing term to the Lagrangian. Gauge fixing, that will be minus 1 over 2 epsilon, just like we did with the covariant gauge d mu, a mu. Now we would just want to add a term that says a mu in mu, like so. And then take the limit psi to 0, then we get the gauge condition that a mu in mu is 0. Now, if we add such a gauge fixing term, then the propagator for the gluon is modified. So a gluon propagator, so propagating with color code A, of course the color code B, mu nu of momentum Q, has a term, the color doesn't change, I over Q squared plus I epsilon minus G mu nu plus Q mu over Q dot n minus n squared Q mu Q nu over n dot Q squared. So the propagator is significantly more complicated than for QED. So with that choice of gauge for the gluons, one can show that the sum of spins for the external gluons, so we will always have an epsilon mu of Q alpha epsilon mu star alpha of Q, like so. When we calculate so m squared would contain such a sum, indeed if we summed over polarization, and that can be replaced, it turns out, with a minus G mu nu plus Q mu in mu plus Q mu in mu over n dot Q minus n squared Q mu Q nu over n dot Q. Now, this of course simplifies if we choose a vector, a nil vector, one that has n squared equals 0, a light cone gauge So then, of course, the last term here vanishes. Now, the reason that it's worth discussing this gauge choice, of course, is that that's actually what's often used nowadays when amplitudes are often evaluated numerically on a computer. So when one calculates numerically, of course, one does not need to square analytically and make such a replacement of the polarization vectors, but one can just choose an explicit representation of the polarization vector, sum over them if one wants to sum, as one does, over all the spin polarizations or spin states of the gluons. But one can calculate M numerically and then square that complex number. So when one wants to do that, one needs, of course, an explicit representation of the spin vector epsilon, polarization vector epsilon. And it turns out that one such representation is, I'm just writing this here because it's used in all the codes you'll need and are already using for evaluating amplitudes. So an epsilon for a gluon of momentum k with respect to a arbitrary polarization or arbitrary vector q, that we call n up here, is equal to plus minus, and I'll use here the notation that one often sees in modern notation for spinners, where I'll just write the momentum q minus plus gamma mu k minus plus over square root 2 q minus plus k plus minus, where q minus or plus is psi bar down or up of momentum q. So that's our row spinner. Gamma mu is the it's a gamma matrix, and k minus plus is our spinner, psi of momentum k up, or sorry, down or up. So if one takes the contraction down here between an anti-spinner and a spinner, one just gets a complex number. Up here one gets a vector, a Lorentz vector, because of the gamma mu, and all of that constitutes one representation of the polarization vectors of the gluon of momentum k with reference vector q. So this is a very efficient representation. It's efficient in the sense that it allows for an efficient evaluation of the matrix element exactly without having to square it. One calculates the matrix element as a complex number and then square afterwards. That's used in MATLAB, comics for Sherpa, etc. We are now ready to investigate the behavior at higher orders in the coupling. So let's say that we are studying a scattering amplitude that has n external legs. That could be Fourier production at the colliders, for example. I draw all the legs here straight. They could be gluons too. What matters here is just the number. So this has 6 legs, 1, 2, 3, 4, 5, 6. So if we were to calculate the scattering amplitude, mn, then it would start with, okay, let's say that this is n equals 4 here. So there are 2 2 incoming, 4 outgoing, then we would get, as a coupling, we will get a lowest order GS N, and then M, let's call that N, because there are 4 final state particles produced, and the coupling is order N. Now, if we were to calculate higher orders here and keep the number of external legs fixed, then obviously, since the number of external legs is fixed, if we emit any gluon from one of the legs, then it has to be absorbed again, otherwise the number of external legs is changed. So that means that there will be 2, since it has to be both emitted and absorbed, there has to be 2 powers of GS in the higher loop correction. So there's a GS N plus 2, M, we want N external legs, but now the coupling is N plus 2. If we were to calculate the next order in the expansion of this scattering amplitude, then again, keeping the number of legs fixed, we would have to emit and absorb any radiative correction. So there will be a GS N plus 4, M, N external legs, coupling N plus 4, and so forth. Now, one could of course calculate the amplitude as well for one extra external leg. So the one extra external leg could be, and then a fifth, right? So this here will start with GS. If N is 4, then here we would have N plus 1, M, N plus 1. So N doesn't change between the 2 examples here. So GS M N plus 1 plus, and then the higher order correction, again by the same argument as before, would have GS N plus 3, because if we keep the number of legs fixed, then any emission has to be reabsorbed. And of course, the amplitude for N plus 2 would start GS N plus 2, M, N plus 2, external legs, N plus 2 powering the coupling, and the radiative higher order loop corrections would be N plus 2, that's N plus 4, M, N plus 2 legs, N plus 4 in the coupling. So if one were to say, let's calculate the cross section, then one would of course need the square of the amplitude. And let's look what happens when we take the square of Mn. Mn square, that's obviously equal to GS to power 2n, and then the Born level amplitude, Mn n squared. Then the next order we get will be, the next order in the coupling will be the interference between this term and that term, right? Let's write this out. Let's delete all of this and write it better. So Mn squared is Mn times Mn complex conjugated. It's a number, so we can just conjugate it. So that's equal to GSN Mn plus gs n plus 2 m n plus 2 plus gs n plus 4 m n plus 4 times the complex conjugate. G here is just a real coupling. Good. So arranging this as a perturbative expansion, so writing first the coefficient for gs 2n, which is our lowest coefficient, that's that term will be mnn squared, mnn squared. Now the next coefficient we'll get is a gs 2n plus 2. And that will arise from that piece and that piece. So what we get here is twice the real part of mnn n plus 2 complex conjugated. And then there will be a gs 2n plus 4, and that will arise from color should I choose? That will arise from this piece here, that piece, and that piece there. So again, we then, I think, get twice the real part of mnn n plus 4 complex conjugated. Then we get a plus mn n plus 2 squared, like so. And then of course the higher order term still that we haven't written out yet. So that would be the perturbative expansion strictly of the 2 to 4 scattering amplitude. For example, if n is equal to 4. It turns out that that's actually not all that contributes to, say, 4-jet production, if we had, say, that the amplitude was indeed for 2 to 4 partons at hadron colliders. There's, of course, the extra contribution where there's an extra real emission that is soft, as indicated here. A soft real emission that still counts to just 4 jets. Now that lives in a different phase space and it's, as indicated, a different amplitude. If we square that one, n plus 1 squared, then that will be equal to gs 2n plus 2 of the amplitude. Let's just write it as a double n plus 1 to power n plus 1 squared, and then of course there are higher order corrections to that, just as we wrote it before, and the next power will be a gs 2n plus 4. And then what we'll have here, if we keep the number of external legs fixed, n plus 1, n plus 3. Right? Because again, we will have to have both an emission and absorption. Sorry, what am I writing here? Here. That was the amplitude squared would of course have then twice the real part of m n plus 1, n plus 1, and m n plus 1, n plus 3 complex conjugated plus higher order, right? And again, there will also be a contribution where we have two soft emissions, m n plus 2 squared, which would be gs n plus 2, sorry, 2n plus 4 m n plus 2 n plus 2 squared. Good. So what we see is that if one calculated the inclusive cross-section for Fourier production, for example, to not just order alpha S4, but to order alpha S5, then there would be a contribution, alpha S, remember, as gs squared over 4. So there will be a contribution from virtual corrections, but there's also a 2n plus 2 power correction from a real emission down here. And if one were to calculate the cross-section to order alpha S5, then one would need both contributions. If one wants to calculate to alpha S6, one would need the contribution from 2 virtual corrections, from 2 real emissions, and 2 real emissions, 1 real emission including the virtual corrections to it. But let's see what actually happens when one calculates an amplitude for virtual corrections or an amplitude for higher orders. Let's specifically look at E plus and minus to hadrons. Right? So we would have E plus and minus to hadrons, QQ bar. So we would have an E minus P1 and E plus P2 and we would have a, let's see, outgoing P3 and P4 for quarks. Now, as indicated, if we're going to calculate the matrix element squared, then we need twice the real part of the Born level amplitude and the amplitude with one loop, with that n plus 2. So let's write down one such one loop diagram. Like so. This is a photon, this is a gluon. And the contribution to the matrix element squared would then be twice the real part of the Born level multiplied by the one loop amplitude. Let's write down the form of this one loop amplitude. Right? So this Feynman diagram here, we would start by a U bar of P3. We will then have a gamma nu. We would have the propagator, fermion propagator along here. Let's say that that will be P3, obviously, let's say that it's the loop momentum that goes around here is p, then there will be a p3 minus p, if p is in that direction there. So there will be a p3 minus p, there's a gamma mu, sorry, mu is not there, then mu is here, that vertex here, there will be a gamma mu, then this propagator here is minus p4 minus p slash, if p4 is outgoing. So there's a minus p4 minus p, there's a gamma nu, that's not gamma nu, yes it is gamma nu. We could write it gamma lambda or gamma sigma, but of course the gluon propagator here would be a g sigma nu, so it would become a gamma nu, and then there's a v of p4. Now of the propagators, we would then have a p3 minus p squared, that's this gluon propagator, and then the contribution from the fermion propagators would be a p3 minus p is this fermion propagator there. There's a p4 plus p squared from this fermion propagator there, and finally the gluon propagator is just p squared. Okay, so the Feynman rules say that when we have a loop momentum like this, we then need to integrate over the momentum p, right? Any momentum p is possible here. But the cross-section would then be essentially a integral over p3 and p4 of this amplitude. The amplitude itself will be, so let's say just write down. So the cross section, there will be a flux factor, there will be some phase-space integrals of something that's called fv, where the fv, the vertex correction here, is equal to the sum of charges like we have at Born level squared, and then there will be a trace. What I've missed out here in this, it's a contraction with a normal electron current at the other side, right? The gamma mu will be contracted with a v of p2, a gamma, if this is mu, then this is mu as well, gamma mu u of p1. So what we will get here is a trace of p2 slash gamma mu p1 slash lambda, and from the other from the quark end of the diagram there will be a trace p3 slash lambda mu p4 slash gamma lambda plus the complex conjugate, and lambda mu here parameterizes all the corrections that we get to the vertex. So that will be gs squared cf, and then the phase space integral d4p of p squared gamma nu of p3 slash minus p slash p3 minus p squared gamma mu p4 slash plus p slash over p4 plus p squared gamma nu. Good. Now all we need to do now is to calculate that loop integral. Unfortunately, this integral here is divergent meaning there's no finite answer. There's a divergence in many regions of phase space. Now, first of all, it's divergent in the soft and collinear regions. So, problem 1, there's a divergence in soft and collinear regions. And what does that mean? That means when P goes soft, or when P is collinear with P3 or minus P4, then this integral here diverges. Not only does the integrand diverge, but the integral diverges too. Now, this is called infrared divergences. Infrared because they are soft, long wavelength problems. So soft and collinear regions give problems. We'll discuss that later. Ignore that. Ignore that infinity for now. Let's look at problem number 2. Problem number 2 is that not only is the integral divergent because the integrand diverges, there's also a contribution for short wavelength that leads to divergent integrals. And that's called ultraviolet divergence. So the problem here is that the integrand, although finite, doesn't fall off fast enough at large P for the integral to be finite. So we can see that it's logarithmically, the integrand is logarithmically divergent simply if we count the powers p of the integrand, right? So for large p, let's look up here, for large p, we see that the integral has 1, 2, 3, 6 powers in the denominator and 2 powers in the numerator. So for large p, the integrand has behaves as p to the minus 4. Now, by changing integration variables at large p, one sees that the integral d4k over k to the 4, that's what we saw was the behavior at large p, is equal to the integral, we just parameterize that in spherical coordinates, so that's the length of k over k to the 4, so, and then a spherical integral, which is equal to 2 pi squared, the integral from 0 to infinity over k. Now this, obviously, integral here, you recognize and see that that's logarithmically divergent in the k to infinity region. So it doesn't fall off fast enough for the integral to be well defined. Now, that feature is actually inherent in all loop diagrams. And as we've seen, it's just a direct consequence of the Feynman rules that we derive from the Lagrangian, that we can't change, and it works really well at Born level. So the question is, what do we do? We have to sort of make sense out of this integral. And the trick is quite simple. So we start by noting that if we reduce the dimension of space-time from 4 to something slightly less than 4, then actually so if we reduce the number of space-time dimensions from 4 to something slightly less than 4, of course there are also fewer momentum dimensions to integrate over. The conjugate number of dimensions to space-time in terms of momentum and energy is also reduced. Now, if we reduce the dimension here from 4 to something d, which is 4, and let's call it something slightly less, something small is called an epsilon, so let's just for convenience call it 2 epsilon. So we reduce the dimensions to 4 minus 2 epsilon, epsilon positive. Then we see that suddenly if 4 becomes 4 minus 2 epsilon, then 3 here, if we still take the 3 out, then what we have here is not 1, but 1 minus 2 epsilon. If we here have 1 minus 2 epsilon, then actually the integral is finite. So if the number of dimensions in the numerator here is reduced, then the integral becomes finite. You can think of it as while the 2k over dk squared is still infinite from the same argument, dk over k squared is finite. We do that, we don't have to take away a full dimension, we can take away just 2 epsilon. For any positive epsilon, this integral then becomes finite. You have to be comfortable working in non-integer dimensions for integrals, but essentially it becomes a question of finding a parameterization of what you would call the unit sphere in non-integer dimensions, and then still apply spherical coordinates. Now, what you would then say is that fine, we've got a finite integral for any positive epsilon. What we need to do is then just to take the epsilon to 0 limit. It would be nice if it worked as simple as that. It doesn't quite. The divergence doesn't just go away by itself. Not this time, anyway. What you'll see, in fact, if one does all these integrals here, is that, and parameterize it in terms of the dimensions epsilon here, one sees that often one will get expressions that contain gamma 1 plus epsilon over epsilon 4 pi epsilon equal 1 over epsilon plus the log of 4 pi minus gamma e plus something of order epsilon. Now, of course, if we take epsilon to 0, then the last term will vanish. But the point is that for any non-zero epsilon, we now have parameterized the divergence of the integral here, or any loop integral, in terms of poles in epsilon. So for epsilon 0, this is infinite or ill-defined, just as the integral is, but for any positive epsilon, we can evaluate all these expressions. And indeed, that allows you to treat not just one loop integral, but define how to add together all the loop integrals. It will all works fine for a non-zero epsilon. But for epsilon equals 0, it doesn't work. What does one do? Well, the point here is that one has to reinterpret the quantities in the Lagrangian. What it turns out is that since we now have well-defined poles in epsilon, then we can add to the Lagrangian so-called counter terms which cancel these poles. Now, that may seem arbitrary at first, and yes, it does seem a little bit arbitrary to say that actually what we thought were the terms in the Lagrangian are not quite the mass term, for example, in the Lagrangian, but there's some bare Lagrangian that gets dressed with perturbative corrections. Now, what we see in a good theory, like QED and QCD, is that one only needs a finite term, finite number, of counter terms for all perturbative orders to be well defined. So this problem here was one that we found at one loop. It turns out that if one adds the counter terms such that the one loop expression is finite, then also the 2, 3, 4, etc., the higher loops are finite. That's a good theory. That's a renormalizable theory, right? Non-renormalizable theories are those where at each order in the perturbative coupling, one would have to add new counter terms in order to get finite results. So what do these counter terms look like? Well, essentially, what we have to do is to use multiplicative. Which just says that every time we see the field B, the bare field in the Lagrangian is actually some multiplicative factor that depends on epsilon times the physical field psi, the fermion field. The same way, all the gluon fields are actually some factor alpha that diverges at epsilon equals 0, some factor z that diverges at epsilon equals 0 times the physical field. Sorry, forget the gluon. So this is called multiplicative renormalization, and the standard model is one that can be normalized, it can be renormalized with multiplicative renormalization and a finite number of terms. In the next lecture, we will see how this treatment of the ultraviolet poles will lead to the running coupling, and we'll discuss how the infrared poles that we haven't looked at yet will cancel when cross-sections are investigated and give finite predictable cross-sections. Thank you.